Okay, so good evening, everyone. So today is 15th August. So we won't be we won't be taking a very full-length class. We'll just be discussing some of the, we'll have for a short period. So essentially, this is the third tutorial session on the NPTEL course on computational quantum mechanics. So I am G.R. Krishnachanavta and NPTEL and a PMRF TA for this NPTEL course. And if anyone has watched the previous sessions or attended the previous sessions, then so essentially the overall idea of this tutorial session is to review some of the important concepts that was discussed in the previous week or in the following week, and then we would also be solving certain problems, if any, something related to assignments and all. Okay, so for today's session, we'll be following the same format. We'll be reviewing certain concepts such as linearization of a function, and then solving solution of solution of nonlinear equations using Newton-Raphson approach. Then discussing a bit about directional derivative, and I'll just be listing down some operations on tensors such as gradient, divergence, and certain integral theorems. And the following, we'll be following it up with a couple of solved examples. Some of them which we can solve using hand, which means that just pen and paper based questions, and then I would just be talking something about MATLAB today, because since this is a course on numerical, what do you call, it essentially involves numerics, and so we need to have some knowledge of MATLAB or MATLAB-like software such as Octave and GNU Octave, or say Scilab and all, and even FreeMat. So I'll be following MATLAB. So if anyone wants, then we can substitute it with other languages such as Python. So it depends on the what do you call on your choice here. And we'll be solving a bit of nonlinear equations. Just one example. I have just written in plural, but just one example using MATLAB. Okay, so let's start with linearization. So I'll just be providing a summary and not discussing in detail. If you really need, then I will actually explain everything in detail, but for now it's just I'll just be giving overview. So what is linearization? And why do we need linearization, right? That's the first question it comes. The thing is, nonlinear problems, right? Are inherently very difficult to solve. Isn't it? So the thing is, we cannot solve it. We cannot solve a general nonlinear problem directly. Unlike say what happens with. So to just save the bandwidth, I'll just turn off the camera. Fine. Okay. So why do we need linearization? And the thing is, linear problems are easier to solve. Linear problems are comparatively, I'm just using the word comparatively much easier to solve. So all the solution techniques are actually designed to solve linear problems. Okay. Now, what we do is, in order to use the all the advantages that a linear problem carries, we actually try to formulate the nonlinear problem as a linear problem. Okay, that's the idea. by some, yeah, by this technique called as linearization. Okay, and then what we can is, so nonlinear problem. So the idea here is nonlinear problem, which essentially is this is formulated as nonlinear set of equations, isn't it? Nonlinear, so nonlinear equations. Then what we do is, and then you have then what you do is treat it to something called as a, this process that we are going to use is linearization. We'll just linearize it. After linearization, we'll have a set of linear equations which needs to be solved iteratively till we obtain the solution, in the desired solution. I'll just call it. Okay. So this is the goal. So this is the process of linearizing that we're going to talk about. And one of the methods to solve this here, this is known as, this method is one of the methods. So now this is called Newton-Raphson method. Okay, so now let's start discussing about linearization from mathematical sense. So what we do is, let's say we have a nonlinear equation. Say we have a nonlinear equation. Okay. Then and it's say given by a form fx is equal to 0. Now you know very well what a nonlinear equation is, right? So if they say that, if and this say if the function is of a form of something which is not of the form of ax plus b, that is known as nonlinear problem. Okay, anything which is not of the form where a and b is an element of R and a is not equal to 0, then it is a nonlinear equation. So you know that you know the vast majority or very huge bucket that we have of nonlinear equations, right? It's a huge set. Okay, so what we do is now what we do is let us try to set up a general idea, right? So the idea here is, let's take a point x is equal to x naught, which is also known as initial guess. And then what we do is we express so what we do is we express the function. We now expand f of x about x naught, x is equal to x naught, using something known as, using a very powerful technique called Taylor's series. Okay, now how is that done? As you may recall from some of the elementary that from your what you call from the undergrad years, that we have, say, any function f can be linearized, can be what you call expressed as a in terms of Taylor series as, say, f of x naught plus first derivative of dr by dx, first derivative with respect at x equal to x naught and x is equal to x naught. Plus half and x minus x naught whole square. And this just goes on forever, isn't it? Because the thing is, Taylor series is essentially we have infinite number of terms, isn't it? Now what we do is let us take x is equal to x naught plus u. U is some quantity, isn't it? Then what happens is this implies that f of x naught plus u is equal to f of x naught plus df by dx at x is equal to x naught, and x minus x naught now is u. Likewise, this term becomes u squared, and likewise, isn't it? So when we say something about linearization, isn't it? Linearization involves just truncating this. So the linearization essentially truncate all these terms which have higher orders of u. Higher orders in the sense that you just look at the powers of u. So this has u to the power 2, and all the other u's with powers greater or equal to 2. So that are all higher order powers of u. So which means that upon linearization, we have f of x naught plus u, and then this is say f of x naught plus. Now you tell me what sign should I have? Is it equal to or approximately equal to? So these are the two options there. The thing is, once we have truncated all the higher terms, now the right hand side is no longer equal to the left hand side, isn't it? So that means that this we cannot use equality symbol. So which means that the left hand side is just approximately equal to the right hand side, because right hand side is not the exact Taylor series representation, isn't it? Or Taylor series expansion. So the thing is, what we'll do is we will just remove this and we'll just have equal to, which will just have a approximately equal to. So this is what we have, what we call as, and this we call as linearized increment in fx at x is equal to x naught. Fine. So this is what it is. Now this term, the one I have just marked square, I mean this just made a box around it. So this term is also written as in a standard notation that we have is x naught. So this is what it represents. And this is approximately equal to f of x naught minus u plus u minus f of x naught. Okay. And this symbol or this operation is known as, or this is how we read it. It's the directional derivative of f at x naught in the direction u. Fine. So we read this as directional derivative f at x naught in the direction u. Now you'll ask me, okay, but the thing is u is a scalar. What do you mean by direction here? So the thing is, we will just be, I'm just introducing here that in this case, direction u is nothing but just a direction along the real line, isn't it? So we have say x naught here, and this is u. So this is nothing but just an increment along the real line. But say when we have a vector, then it becomes, then it tends to have some sort of a direction, isn't it? That we can only proceeding along one particular, along some particular increment in u, or some particular increment along that u. So it's just a multiple of u. So that's what we call as direction. Direction in the sense that we are just incrementing something as a multiple of u. So you should just remember that, what you call the understand, or you should just have an understanding of this particular statement in that language. Okay, that we are just looking at how f changes at x naught in a particular, along a particular u. So that's what I'm trying to say here. So in this case, since it's a scalar, so we just have how f changes along this direction, and that is known as direct. So that is what is meant by this operator here. Now we can actually express this operation as something like this. You just have a d by d eta of f at x naught plus eta u, and at eta is equal to 0. So this is the operational definition of the directional derivative for a, this right now we just have a scalar function, so that is how it is. Okay, now let's just try, let me just try to invoke, just try to bring in the what do you call the Newton-Raphson method here. Okay, let me just try to introduce it. So what we had was, we had f at x naught, or say fx, or I'll just call it say f of x naught plus d of f at x naught in the direction of u, that is equal to, I'll ask me, okay, now let me actually try to avoid this, where this comes. So initially we had f of x naught of fx is equal to 0. This linearization gave us this, isn't it? Where x was some, x naught was some guess point. Okay. Okay. So now what we'll do is, and going back to what I had said, that when we linearize it, we just have to solve linear equations multiple times iteratively till we obtain the desired solution. So the thing is, we have started with some initial guess x naught. After this, you will get a value of, this will give us a value of like, now let me just write it again. What do you call that? Even the expression for df by this one, this is nothing but df by dx at x is equal to x naught and into u, isn't it? This was equal to 0. Mind you that they were just approximately, okay? It's just approximately equal to 0 essentially, because these are just approximately. But I mean, right now what we are doing is, we want a quantity such that it satisfies. So we want u such that approximately becomes equal to, okay? But the thing is, it won't happen in just one step. We'll have to do it multiple steps. Theoretically, we need to do it multiple steps, okay? So this implies that U is equal to, by all this doing all that what you call just transpose of the quantities on other side, right? So this gives us minus f of x naught divided by df by dx at x context. So you have u. Okay. Now what you do is, this is just an increment. So you have gotten what you call a new value is x1 is equal to x naught plus u. So we are incrementing. However, when you put back into the what you call as an argument of the function x, this will still not be equal to 0 in general. So what you do is you again linearize about this. I'll just start the final version. So it's df by dx, x is equal to x1, u is equal to, and keep on doing it. So this will again have, we'll have u is equal to again, so f of x1 divided by x. Okay. And then we'll increment x2 is equal to x1 plus u. Fine. And likewise, you go and on, and then we have, say, at some iteration level, at kth iteration level, what you have is f of x1, sorry, f of xk plus df by dx at x is equal to xk, and into u is equal to 0. Fine. So what you have here is that u is equal to minus of f of xk divided by df by dx at x equal to xk. Got it? Fine. And then we will just be carrying out this operation, and then once we have this, we'll again augment x1 xk plus, and we'll just carry this operation, repeat till f of xk is equal to 0. So that is the idea. Just keep on doing it, isn't it? So that is how Newton-Raphson approach is essentially used to solve nonlinear system, isn't it? Okay, so this was just about single variate system, like when we had just one what you call variable in the function, or the equation was in terms of just one variable. Now say what we have, what if we have a set of n number of variables? So the extension to, let me just pick up a new slide. Now say extension of Newton-Raphson method to nth order equations, or nth order system, or you can say that to a system of n nonlinear equations, where n is the number of nonlinear equations that we have, and also it's implied that we also have n number of variables. Okay. Now what we do is, for that we are given some, say, g vector. I'll just denote as g as a vector, so that is just an underscore, and x also underscore is equal to 0 underscore. Right? So this is, so x is an element of Rn, where means that it belongs to a to a space of dimension n, isn't it? In real numbers, defined over real numbers. That's what I meant to say. And likewise, G here is a mapping from Rn to Rn. because things number of arguments it takes is n, and the number of equations that it produces is also n, isn't it? So this is what I am trying to say here. So in this case, we'll just be describing what you call in a similar format. Just say let's linearize it. Likewise, we'll start with say x naught, and now this x naught is a vector about x naught as a vector of Rn. Right? Then we have g, this one, plus. So the thing is we are linearizing approximately, right? Plus d of g vector at x naught vector in the direction of u vector. Now u vector is also an element of Rn. Fine. And we expect the same thing, that we would like to have this almost equal to 0, isn't it? So we'll again make this approximately equal to 0, and then solve for the system of equations ideally in the same way. But here what we do is, before that, now we need to derive the expression for this, right? No, it's no longer it's not as easy as that was the case for single variable set of single variable equation, right? You know, derive the expression for this directional derivative. So what we do is, let us define quantity as, say, let's have x vector is equal to x naught plus eta u vector. Fine. Now eta here is a scalar. So essentially, what we are saying is that we don't know the value of, we don't know x vector. However, we started with some x naught vector, and u vector is some direction in which we would like to increment, or u vector is the increment that we want to compute, isn't it? And eta is the variable, is the step along that particular vector that we need to take in order to satisfy this. I mean, in order to what do you call, in order to satisfy this equation, that let's say x naught plus eta u vector, this will be approximately equal to 0 vector. Okay. However, for operational sense, we'll just make it 0. Right? This is our goal here. Now, now what we do is, let's define a function. I'll just call it f as a, and f again and okay. So here let's define something called f vector. So f vector is defined as eta is equal to g of x naught vector plus eta. Now when eta is equal to 0, g vector, it's just g of x naught, right? So what we do is, now this is as if we are solving for a, so okay. So the goal here is, we need this definition in order to obtain our directional derivative. Now I'll ask me, okay, why are we doing this? The thing is, u is something which we need to compute, or provided that at first we assume that u vector is known. Okay, so then it becomes as if we are dealing with eta. Okay, as if eta is our variable. We assume, okay, let me tell you. So x naught is known, isn't it? U vector is assumed to be known for now, assumed to be known. And eta is considered to a variable. Now it looks like as if we have a system of equations, but in just one variable, isn't it? So as if just eta is a variable. Now what we do is, now we can easily use Taylor series expansion, isn't it? Now you understand the idea, right? Because Taylor series expansion was actually obtained for just when there was just one variable, isn't it? The Taylor series expansion of f eta about eta is equal to 0. Fine. So what we'll do is f of eta vector, this is vector, is equal to f vector of 0 plus df vector by d eta, eta is equal to 0 into eta plus half of d squared of vector by d eta squared at eta is equal to 0 and eta squared plus dot dot. Now for the purpose of linearization, we'll do the same thing. This will truncate. This is called as truncate. We are not ignoring it. We are just truncating it. Truncate this such that what we have is f of eta is approximately equal to f vector of eta plus df by d vector at eta is equal to 0 to eta. Fine, approximately equal to. Fine. Now what we do is, so we have our Taylor series expansion. Now let's replace f vector, the definition of in terms of the actual set of equations that we had. So it's like g vector of x naught plus eta u vector approximately equal to g of x naught vector plus d of g vector divided by d eta, isn't it? This is at x naught vector plus eta u vector at eta is equal to 0. Fine. And again, this is what we call as our directional derivative. Of g vector at x naught along u vector. Now we'll do some trick so that we can bring this in the same form when we had for that of the case of a univariate function, right? In the univariate case, we saw that it was just x naught plus u. So that can be done easily, isn't it? And here there was again multiplied with eta. So yeah, so that was done easily. Isn't it? What we did was, I'll just go back in just to show you. Now you see that there is no unknown quantity in this, right? I mean, in the sense that we don't have any extra parameter here. So likewise, what we'll do is we'll try to eliminate eta. So all that we need to do is take eta is equal to 1. Then what we have is an equation of the same form as that for a univariate case. So we have g vector of x naught plus d by d eta g vector x naught plus eta u vector at eta is equal to 0. So now we have that the operational definition of a directional derivative for a vector valued function, isn't it? So what we have here is, now we can write this as comparing this equation, this one with this one. Now you clearly see, right? So that we have we are now able to obtain the expression for dg vector at x naught in the direction of u vector. This is equal to d by d eta g vector of x naught plus eta u vector at eta is equal to 0. So this is the operational definition, in the sense that using this definition we can obtain the expression that we are very much that we are looking for, isn't it? Okay. So so that was essentially the aim here. Now we can have our g of x naught vector plus d of so I will just write this expression here, x naught vector. The x naught, this will be equal to set to 0, and then eventually following the same process, we would want let's have at kth level, kth iteration level, we'll have g vector of xk vector plus dg at xk vector along the direction u vector is equal to 0 vector, and this you can write as d of g vector at xk vector u vector equal to minus g vector of xk vector. Okay, so essentially using after solving this equation, we get this upon solving this equation results in u vector. Then this implies that x vector k plus 1 is equal to xk vector plus u. Fine. And then we just keep on iterating it till we have some solution. So essentially, it just goes on 0, 1, 2, likewise, till we have our desired solution. So this is what we had, what we called as our. So we have covered directional derivative, how to solve linear system equation, and then also did some what do you call discussed about Newton-Raphson method, isn't it? Now, reviewing this further. Now let me talk about operations on tensors. So my goal here is just to review. If you have any problems, so just please let me know. Maybe through chats. I mean, what do you call? You can just post a message on this meeting link. So then I'll just be reviewing. I'll just review and try to address that problem. Okay, so now let's just discuss about certain operations on tensors. So let's start with, first of all, let's talk about gradient. Let's start with gradient only at first, isn't it? So first of all, let's talk about the gradient of a scalar field. In 3D space. Now, why I'm talking about 3D space? Because this is where all the engineering systems are located in, right? I mean, they all exist in 3D space, isn't it? And in this case, where the gradient of a scalar field, say you are given f. How do you determine it, and what does a gradient mean? So we can also write the directional derivative of f at x naught vector along direction u vector as something which you must have studied in high school, right? In high school, I mean in higher secondary school, in class 11 and 12, right? So here this can be written as gradient of f at x naught vector dot. Now I'll ask me, okay, what does this mean? So let me just try to explain it. So gradient essentially tells about, what does it mean? Gradient is nothing but some change, right? Some change. So it is rate of change. No, rate of change with respect to what? So it's rate of change along space, isn't it? So now you must have heard about color gradient, right? I think I'll just give you from a very rudimentary example. So say I'm just placing bars in this just to signify some color. So initially it is very what do you call initially they are just placed far apart, and then gradually as you go, the number of lines just keeps on coming closer and closer, closer and closer. Okay, and then eventually you won't even find spacing between two lines, isn't it? So this is just what is gradient. I mean, I'm just trying to make you understand the concept gradient. Now, what you see is initially the distribution is very sparse. As it proceed along this, say let this direction be x, and this belong y. Okay. So what you see is as you proceed along x, the number of vertical bars keeps on now you'll ask, what do you mean by number? The thing is number contained in some unit dimension. Let this be some unit dimension, 1 unit. So what you see is in 1 unit, it was just one or two lines here, one or two bars here. As we keep on increasing along x, we see the number of lines or number of bars keep on increasing per unit, isn't it? So the thing is, there is some gradient that we are seeing. Now you understand. Now just try to understand the meaning of gradient here. Just try to just imbibe the idea from here. So this is known as what we call, as we progress along x direction, we find that the number density of vertical bars keeps on increasing. So which means that there is a gradient in this direction. Gradient increases in this in this direction, means in x direction. Or write there is, or otherwise just there is a gradient in x direction. Now let's take about now let's just study I mean consider the y direction. So we just place unit spaced intervals along y-axis and just count the number of bars. Is there any bar along this line? Any vertical bar? No. Even if you just have a segment of every bar placed along this direction, right? Just segments. Now what you see is in every unit interval, the number what you call the number of segments along y direction remains the same, no matter which segment you choose. So the thing is, in this direction, there is no gradient. So I hope now you have understood the meaning of gradient. Okay, so it's just how rate of change of quantity along some direction. I mean, rate of change of quantity, that is known as gradient. But you need along what? You need to define what do you mean by along what direction there is rate of change. So for that, we need the concept of directional derivative. In order to measure the gradient, we need certain directions. So then say along u vector, like in this case, I have defined x and y directions, right? In along x directions, we are finding gradient along y direction. So what we saw in x direction was gradient, in y direction, there was no gradient. So just like that, we just have this, what we call as directional derivative, isn't it? So we are finding gradient in some direction. Okay. And now you clearly see the relation between the gradient and the directional derivative essentially. And now you'll ask me, okay, but how do we find it? For that, all we need to do is now let's try to get what this operation means. Now what we do is let's determine the expression. what determine the operation. So for that, say we start with our f of x naught vector u vector, and here x naught vector is an element of R3 because we are living in 3D space, right? And this using our definition from the operational form of the x naught derivative, we can have at f of x naught vector plus eta u vector. Again, u is also an element of R3. Now what we do is we can use something called as a chain rule. I'm sure you all of you are very familiar with this. Now what you do is in chain rule, what you do is, or before that, if you ask me, before that, what we do is, so we need to have what you call, about partial derivatives and all that. Before that, what you need to do here is we need to have del of f at x naught vector plus eta u vector divided by del of x naught 1 plus eta u1 dot del of x naught comma 1 plus eta u1 divided by eta. Likewise, and this is all eta is equal to 0. Plus similarly for the second component, I'm just trying to say that, yeah, since x naught lives in 3D space, so it will have 3 components, right? So you'll have u2 and again x naught plus eta u vector. Eta is equal to 0 and x naught comma 2 plus eta u2 divided by eta and eta is equal to 0. Likewise for 3, one more term will be there. All of which we can write in terms of a summation as summation of I is equal to 1 to 3. Okay. And then we'll have partial f with respect to. And now what you see is the thing is it involves operation with respect to this. However, you don't find after doing the operation, what you'll see, right, is that all we are what we are doing is you can just have this as a f naught. When we put eta is equal to 0, this simply implies that we are having this as x1 or rather xi, and eta is equal to 0 simplifies that we are just have x naught comma. And likewise here it becomes taking derivative with respect to eta gives us nothing but ui. Okay. And now you can clearly see that. Now what we need to do is you can see that it's as if there is a we see, right, there is a one in repeated index here. So this simply means that there is some summation involved. So there is some quantity dot u. You can see it, right? There is a summation implied over I. So it's summation implied over I. Okay. So now comparing is equal to something dot u. Or in this case, it was so we'll just copy that, right? So it is just around summation of I is equal to 1, 2, 3 f by x I at x I is equal to x naught comma I ui. So after this, what we can clearly see that, and so I was talking about canonical basis, right, from in the previous lecture. So what you do is let's take u vector is equal to e1, e2, e3 in succession. So then what you have is, so our goal is to find directional derivative along e1, e2, e3 axis. is this gives us, in this case, u1 ui is nothing but just 1, isn't it? So we'll have okay, let me first write. Let me just try to explain to you what happens. For u vector is equal to e1, this implies that u1 is equal to 1, u2 is equal to 0, and u3 is equal to 0. Right? So what we'll have is x naught dot e1 is equal to, we'll just have partial x. Fine, you can see right clearly. Likewise, for this, we have u1 is equal to 0, u2 is equal to 1, and u3 is equal to 0. So in this case, we'll have the third one is e3. Then this means that u1 is equal to u2 is equal to 0, and u3 is equal to 1. So we'll have the third comp. I hope you are understanding. You have figured out what I'm trying to convey here. So what I'm trying to say that from this definition, you can clearly see that the grad f at x naught, the first component is, and likewise, isn't it? So you can clearly say that when we express it, right, in terms of its indicial notation, so we'll have at x naught vector is nothing but summation of f by xi at xi is equal to x naught I into ei vector. So now you understood the meaning of gradient, and in terms of indicial notation, we can also write as grad f vector is equal to f comma I comma indicates partial derivative into ei vector. Fine. Now what if f is a scalar? Sorry, f is a vector here. In that case, all that we need to do is say f is a vector. What do you call, yeah, f is a vector field. In that case as well, we'll have the directional or the gradient of f vector at x naught is nothing but directional derivative of f at x naught vector in the direction of u vector. Fine. And using a similar operation, right, we can have of f vector is given as summation of I is equal to 1, 2, 3, provided that we are x naught, this f vector is defined over 3D space. J is equal to 1 to 3. Okay, now you'll ask me, okay, this is fine, but just give me something which is easy for me to just a simple operator in terms of indices. That's what you'll ask me, right? That it looks like some, I don't want, I just want to understand the pattern such that I can apply this grad operator on any nth order tensor, isn't it? So what I'll do is, this operation is also defined as the gradient of any quantity is defined as partial x xi that quantity with a tensor product. Fine. So this is the operation form. Operation. Now here I can be equal to 1 to 1 to till d, where say here such that it belongs to. So this grad operator maps something. Let me leave it as it makes more complex here. So here d simply indicates the dimension of the grad operator. Say if grad operator is in 2D, then you'll have d is equal to 2. If it's in 3D, that's grad is equal to 3. And if it's 1D, then you just have a single operation, right? So this is what I'm talking about. So this is the operational form. So d here indicates dimension of grad operator. Now beautiful thing here is using grad operation, we can define something known as a divergence. How do you define divergence? So the divergence in terms of operational form is divergence of something is equal to sorry. So the divergence of something is parcel of parcel xi, that quantity into ei. Right? Now let me give you an example so that you are able to understand it clearly. And this is also defined as ultimately from a definition point of view. This is the operational form. This is operational form. That how you actually compute it. This is operational form. But how do you define it? The thing is, definition of a gradient divergence is divergence of something is equal to trace of the trace of the grad of that quantity. So this is the definition. And this is the operational form. Fine, this is the definition. So what you are able to see is that due to in gradient operation, we find that there is a dot product involved. So what does this dot product do is it increases the order of the tensor. So if you are having an argument as first order tensor, then it becomes grad operation makes it a second order tensor. And if it's a third order tensor, it becomes fourth order tensor. However, in divergence is the opposite. So if it were a first order tensor, the divergence on that would give us a scalar. If it is a second order tensor, taking divergence gives us a vector. You see that? So there is a reduction in the order of the tensor after operation. Now the third thing that we had wanted to discuss is integral theorems. So just a minute. Okay, so we are talking about the integral form, isn't it? So We'll talk about two integral theorems. Or I think in the second week we had just talked about one integral theorem. Okay, so I'll just stick it to that. So what we are doing, trying to derive is what does integral theorem essentially do? So suppose you have a body. Suppose there is a body B. What does integral theorem do is you just want to express a quantity which is defined over the body in terms of an integral over the surface. So this is a dA vector. This is a unit normal for some small paths with that's all. So it's area with magnitude dA, and its unit vector outside is given by eta. And the covering of this body or the envelope is known as is also in mathematically represented or by parcel B. So parcel B indicates the boundary of B. So if it's a 1D, just I'm taking a digression here. So if it's a line, what are the boundaries? The boundaries are the endpoints. If it is a 2D object, what are the boundaries? The boundary is the line, is the curve which encloses the area within. If it is a 3D body, so let's take a simple cube. What is the boundary? So the boundary consists of all the 6 faces. So this is the boundary. I mean, all the 6 faces. 6 faces are the boundaries. In this case, it's just the perimeter is the boundary. In this case, endpoints is the boundary. So you understand, right? I just please just visualize it, and then it gives us an idea about. I'll just call it as a notion of boundary. This is in 1D, there's in 2D, there's in 3D. So yeah, so let's have a general. Let's let it be. Let us what do you call, let this body exist in 3D space. Given E2 and E3, isn't it? Now say when we are so the goal here is to relate any quantity to any quantity defined over the volume to something over the boundary of that domain. So say what we have is, so it relates integral of a quantity defined over volume to that of integral defined over surface, or what you call as our or boundary of the domain. So say we have a scalar field F. So we have, say, scalar field, we have defined over volume B, and likewise having a boundary parcel B, right? So then we can then the integral theorem says that grad of that scalar over the volume, dV indicates an infinitesimal volume within this body. This is equal to parcel B F eta vector dA. Okay. Now, if you ask, okay, what if we have some other field defined over the volume? Then say if F is a vector field, then in that case, you'll have F dv, this is called parcel B. Then we have F vector, tensor product with dA. Fine. Now, taking divergence of just the thing that we just defined now. Not taking divergence, we are just taking trace actually here. Taking trace of this. Let's take trace on both sides. So the thing is trace of, now the thing is we can take the trace operator within, right? So it becomes integral over domain. So trace of dv, this is equal to parcel B, trace of a vector cross one with n. And now this, as we recall, not this, I mean the integrand of this expression. So this is nothing but divergence of f, right? That's what we had looked at from our divergence relation, isn't it? The divergence is equal to trace of grad. And then, and the second property that we do is the trace of a tensor product of two vectors is nothing but the dot product of the vectors. So this means that what we have is B divergence of F over dV is nothing but parcel B F dot n vector dA. From this is the widely known Gauss, one of the most widely known integral theorems in quantum mechanics, Gauss divergence theorem, if not the most widely used. Okay, so this is what, yeah, I think we had reviewed whatever was to be discussed. Now let's solve a bunch of problems, and just a problem, we'll just solve one problem today. Let me just take a problem. Okay, so say you have a vector say v, and that is defined by as x1 x2 e1 plus x2 x3 e2 plus x3 e1. The goal is to determine grad of v vector, then determine first invariant of grad v. Before that, let me just write some pointers and take some point. Consider a point A, which is at say 1 0 0, and determine the first invariant of grad v at that point at A, and also the third invariant grad v at A. Okay, so let's solve the problem solution. So this is the question and the solution. Now what we do is invoking the operational form of gradient, right? This is nothing but partial xj of v tensor product with ej, isn't it? So then this is equivalent to writing of as if partial vi by partial xj ei and this we can write in matrix form as here I is equal to 1, 2, 3, and j is equal to 1, 2, 3. So this is how we can write it, right? So this is v1 by x1. Let me make a bigger box. I mean, bigger is quite I think. v1 by x2, x1, v2 by x. Sorry, we'll have I constant, right? So it is v1 by x2, v1 by x3. Likewise, v2 by x1, v2 by x2, v2 by x3, and v3 by x1, v3 by x2, and v4. Sorry, v4. V3 by x, and this indicates that it's EI because we are in operating. I mean, EI and EJ as are or the canonical basis. Right? So let's do it. So partial with respect to x1 is now this is v1. These are v2. This is v2 and this is v3. So partial v1 by x1 is x2. Partial v1 by x2 is x1. v1 by x3 is 0. There is no x3 component there. I mean x3 factor in that term. And v2 by vx1 is 0. v2 by x2 is x3. v2 by x3 is x2. Now v3 by x1 is x3. v3 by x2 is 0. Why? Because that v3 doesn't contain x2 as a factor. And then v3 by x3 is so. Okay. And at point P, sorry, at point A, you have grad V at A is given as so it implies that x1 is equal to 1, x2 is equal to 0, and x3 is equal to 0. So x2 is equal to 0, x1 is equal to 1, and then x3 is 0, x2 is equal to 0, and x3 is 0, x2 is 0. Sorry, x1 is 1. So wherever apart from x1, all the other terms are 0. Now let's just call as B matrix. Okay, B matrix or B tensor here. So just call B tensor, but this is the matrix representation of that. Now, so the first question is first invariant of B. What is the first invariant? First invariant is also called trace of B vector. So trace of not B vector, B tensor B. So trace of B is nothing but B I. Isn't it from the definition? So Bi is, when we express fully, it is B11 plus BT2 plus B33. Now from the matrix here, B11 is 0, B22 is 0, and B33 is 1. So this is 0 plus 0 plus 1. So this becomes 1. Right? Now the second thing is third invariant. It was asking, isn't it? So what is the third invariant? Third invariant is also called the determinant. The determinant of B. So I'll just write here. You know very well how to compute determinant, right? For the 3D system, for the 3D matrix, 3D third order matrix, is part metric 0, 1, 0, and we have 0, 0, 0, and we have 0, 0, 1. So let me expand along third axis. Sorry, along the first. Let us expand along first column. You know that we can do that, right? So I'm just expanding on first column. The trick being that in this along this column, all the terms are 0. So it means that we'll call this B11 into minor, or rather B11 into cofactor of B11 plus B21 into cofactor of B22, or B21 plus B31 into cofactor of B31. Now ask me why I'm doing this, why I'm taking first column. You know the answer, right? What is the value of B11? This is 0. What is the value of B22? This is also 0. What is the value of B3? This is also 0. So I don't care about the cofactors. I don't need to compute it. Why waste energy, right? So all we have is 0. Now, if you say expanded along the first row, then you would have 0, 1, 0. So you would have to determine the cofactor for 1. Isn't it? Because it will be 1 multiplied by cofactor by its corresponding cofactor. So we have chosen such an axis that all the terms are 0. So the determinant of the vector is B tensor B is 0. Okay, so yeah. So we had also something in line to discuss today, right? I'll just delete all the slides. Maybe I'll do it later. So our next goal was introducing MATLAB. Okay, so I'll stop sharing from here, and I'll share from. So I'll share from. I'll share my laptop screen. Let me just open some. Learn MATLAB. Rather, I'll just clear it. I'll just clear, and I'll just. I'll just give a brief introduction today. We'll concentrate in the next. I mean, if anyone wants to discuss about it. So MATLAB is essentially the full form of MATLAB is MATLAB is matrix laboratory. So the thing is, it was developed for doing complex operations on matrices. So that's essentially the goal for the. I mean, what the MATLAB is intended to do. So initially we can use MATLAB as a calculator. I'll just start. I mean, I'm just discussing what a generic tutorial class for MATLAB looks like. So it's a 1 plus 3 is equal to 4. You guessed it. Now 1 divided by 3 is equal to 0.333. And say 4 divided by 2 is 2. 4 minus 2 is fine. Now there is one way of doing things. Otherwise, we can also assign values to certain variables. Say a is equal to 4, and if I use semicolon, it will suppress the output. Say now, if I press enter, you'll see the value of p. Now, say if you are say adding something, then a plus 1, the answer will be 5, right? So this is it. Now you say you want to save this, so it will be a plus 1. Now it will be saved in b. Okay. Now you can have a plus b is equal to 9, isn't it? So this is just like when you, I mean, as if you are using MATLAB as a calculator. Plus, I'll just give a fast review. So say in if any one of you is aware of any programming language, then we have something known as loops, isn't it? Say I want to print something 5 times, or I want to say print is 1 to 5. One way would be to print 1, 2, 3, 4, 5, but that's not what we would do. Say if we would be wanting to print 1 to 10. So in MATLAB, printing something is just putting article using this command called disp. You can have say disp4 will give 4, isn't it? Now say disp A will give us 4. Disp is a display, so disp5 or B will give us 5, isn't it? So you can also define operations within it. Say A plus B will give us 9. Now say we want to print 1 to 10. I could have used disp 10 times, but the other way is, why don't I define a loop? So 1 is to 10, 1 is to 1 is to 10. So the first here implies that we are starting with 1 increment of 1 till 10, and then we'll have disp 10 or disp I, and then we need to, we can just use semicolon to anywhere. Disp will eventually give us the output, and then we need to end the loop with end. So you see 1 to 10 is being printed here, right? Okay, so this was one thing, and so this is, so what we'll do is we'll just solve a simple problem. So of say Newton-Raphson problem, right? Edit. I'll just use NR solve Newton some problem. Okay, Newton-Raphson solver. I'm just writing a script so that I don't have to type everything in the command. This is the command window. So say solve a nonlinear system using Newton-Raphson theorem. So the nonlinear system is say f of x is equal to say x squared minus 3 into x plus 2 is equal to 0. Now I'll wonder what are the solutions. Now the thing is this after factorizing it, right? So the analyticals, this you can factorize it as x minus 1 into x minus 2. So it has two solutions, right? So this implies that I'll just call it analytical solution. So this implies that x is equal to 1, 2. So these are the two solutions possible, right? Okay. So what we do is let me set up the problem. At first, let me define something called as a function. I'll just define functions. So let me have two functions. So in this is how we define function in MATLAB. So function. So say I want just the value f. So f is equal to. I'll just use say val. Value means value of some function f. It takes an argument x, and then what it does is it does val is equal to, it calculates the value of function. So value is nothing but, just copy this and paste here, and then it will return that val. And the second thing we need, right, in Newton-Raphson we require two things. Let me first write how do you operate. So Newton-Raphson works on the principle of, so how do you carry out numerical solution? Now in that case, what you have to do is we'll have xk plus 1, or rather so u is equal to minus f of xk divided by df by dx of x. This is what we are doing, and then increment will be x of k plus 1 is equal to x of k plus u. This is what we are doing, right? So in that case, you require the derivative of f at x as well as the value of the function itself. So there are two ways. Either so I'm just doing one simple way, right? Okay, sorry. Yeah, unlike C++ and all, you don't need quite to do this. Okay. And the second function that we'll do is so this returns value of f at x at x. And the second thing what will it's also return, it will return df by dx at x. Say in this case also we'll have val is equal to, now you take the derivative of this, so this gives us 2 into x minus 3, isn't it? So what you'll do is you'll return it just needs to, yes, see that rather not return in this and so and in MATLAB and denotes that some operation is completed. Fine. Okay, now once we have that, so now let's construct, let's give some initial guess. Say x is equal to, so say x naught is equal to whatever you say. So it's 1 or 2, right? So let's take 0.5. And let's what do you call have something known as x is equal to x naught, or rather xk. So what I'll do is initially we'll start with k, and here initial guess is, I'll just call it k is equal to 0. Fine. And then you'll have xk plus 1 is equal to xk minus plus u. Now you'll ask, where is u? Okay, so let me define u. U is equal to minus of, we'll call this f of xk divided by df dx at xk. Right? We have this. Now we need to do is we need to keep on iterating this. But you will say, for how long? The thing is, you know that in computer systems you can never. The thing is, you can never have the exact answer, isn't it? So the thing is, if we say if we don't say, no, the thing is we need to loop this over. So you can have for I is equal to 1 is to just leave blank. This won't work. So what we just let's try, use another loop. What we have is while loop, and then have just non one value. One means that this has it will always have some non-zero vertical argument, and this loop will come. And at the same time, what we need to do so what we are doing is our I'll just comment things out. So we are doing increment in x, updating, rather adding increment to x, increment u, adding increment u to k, and then update xk. So it as xk now will be equal to xkt. Right. I'll close this and I'll just do end. Now the thing is, if I run this loop, right, and I'll also have, say, I'll just print solution. So it has this. Escape. Now, what if I run this loop? Let me just run. You'll see that it will never end. See, it already reached a value of 1. It will never end. So I'll just stop this. The thing is, I need to put some stopping condition, right? Otherwise, this loop will keep on going forever. Even if you obtain the result, the computer on stops solving it. Since this is since we are doing some iteration, right? We need to add something called as a breaking criteria or the stopping criteria. So this was essentially loop or maybe iteration, carry out iterations till solution is obtained. However, we just saw that no matter even if you carry out iterations till solution is solved, is obtained, it doesn't stop. So the thing is, now we have to define something known as a tolerance. Like I don't want the exact answer. I just want something which is so the difference is very close to 10 power minus 6. So which means that I don't want fx to be exactly equal to 0. I just want f(x) of fx give something f of x such that f of x is equal to the tolerance. So I just want something such that f of xk is approximately tolerance. Fine, this is what I want. And then, however, I just want something. I just want residue. Residual is nothing but that same value. Say I'll just call residual to be equal to some 1 for now. It's just the starting residual. Just so that our loop starts. So what I'll do is I'll just say residual is greater than tol. So if the residual is greater than tolerance, this loop will go on and on. However, once it falls below the residual, it will stop. But you'll say, okay, fine, but I don't see residual being updated. It's always 1. Okay, so what I do is, after I have done all that, I will just compute residual at the last or other even before. And just compute residual. Now, say residual is nothing but the function value, isn't it? So you'll have residual is equal to f of x kp1. This is being updated. Now loss fine. What if it's negative and all? The thing is, if it's negative, then it will exit the loop, isn't it? It can be positive or negative. So what we do is it's the standard practice to take the absolute value. This is the absolute value. So we want it to be greater or equal to just in the vicinity of 0. It's either plus side on the plus side or minus side. So then I've taken absolute value, so it will only consider the positive values. Now what you will say is, now this loop won't run forever. I can show you that. Muchik, everything is right. Okay, things seems to be right. Okay, display k. I just want the solution kp1 actually, and the residual. Now the thing is, if the residual is being computed. Now the thing is, let's see how far it runs. Okay, sorry, I have done something wrong here. Okay, sorry, xkp1, yeah, absolutely fine. See, We gave in the initial value was 0.5. In second iteration, the value becomes 0.875. Third becomes 0.9875. Third 0.998, and becomes 1. After 1, it just stopped, isn't it? So this is how we do looping. So the thing is, we can just write this. The solution is, and I actually want to place the solution in one line, and the solution is num2 str. It means that number 2 str xkp1. And eventually you see that both have the same value, so no matter what you write, it works. And then close it. Now I'll say that solution is 1. Fine. Now there is what you can do is you can even stop printing the solution. Just have the final solution. So yeah, the solution is 1. Now I'll say, well, fine, but what if I need to? I want to find the second answer. So second answer, then you have to change xk value. So say if I start from 1.5, let's see where it drops. The thing is, it's divergent. Now we need to check why. Why does it? Why if you put 1.5, it diverges? Look at the value of the derivative, which goes in the denominator of to find u. When x is equal to 1.5, it becomes 2 into 1.5 is 3 minus 3 is 0. That's the reason. So what we need is just a little bit put x on. So the answer is 2. Now say, what if I want to have 4.9? Then where should it land? I suppose it should land at 1. Yeah. So 1.5 on the either, if you go on the left hand side, it will, the solution will result in 1, and if you're on the right side, it will become 2. So that is the. In this case, the solution happens to well separated. So if you have say solution to be multi-valued and in the close vicinity, then it becomes a problem. Then we cannot use the current Newton-Raphson in its current form. We need to, otherwise it will just keep on oscillating between the two, and the what you call the code will never stop. So then in that case, we need to modify that Newton-Raphson method, and then we need to use a modified version and then implement it. So yeah, that was my aim here for today's session in terms of introducing MATLAB to. Okay, so what I'll do is I'll just calling it a day for today's session, and let me stop sharing it. So okay, so we'll be meeting again on for the next session, which is tutorial session number 4 on the upcoming week, which is 22nd of this month. Okay, so yeah, bye.